Thank you. It was about 5 years ago, almost exactly 5 years ago today, that Google made a rather startling announcement. This was how the BBC reported it. They had achieved quantum supremacy. Do you remember this? They had claimed to solve a problem on a quantum computer faster than it would be possible to do in a classical computer by orders of magnitude. They said they'd done in 200 seconds a task that should have taken 20,000 years. Obviously, this was interesting and exciting. The press was full of it. So was the scientific press. This is how Nature and New Scientist reported it. And everybody was talking about this, and everybody was asking the same question. More specifically, what exactly is a quantum computer anyway? What exactly did they do? And should I be interested in it? Well, spoiler, yes, you should be interested in it, because this stuff is really happening. It's not science fiction, and somebody has to program these things. And who, if not you? What exactly did they do? Well, they solved this problem in 200 seconds, which they said would take 20,000 years. But IBM said, oh, no. IBM were also in this space, by the way. They said, we could have solved it in 4 years. As if that was going to spoil their achievement. Well, what exactly is a quantum computer anyway? Well, you're in the right place. I'm going to tell you exactly. Before we can talk about that, though, we have to talk about why there is any motivation to build a quantum computer. So, probably you know most of this stuff, so I'll go through it really quickly. There's a whole category, there's a whole hierarchy of problems that we can solve on computers. It's the theory of computability and complexity. There are trivial problems. These are problems which you can solve on a finite state machine just by feeding data in and reading the results out. These things have no memory. You just feed it in and watch the state change. But there's a category of problems bigger than that, which is the ones that we're generally interested in, which are the polynomial problems. These are problems which do involve memory, and you can solve them as the problem gets bigger, then the length of time or the amount of memory that it takes to solve the problem also gets bigger, but it does so in a controlled manner. This is why they're polynomial problems. The next size up from that are the non-polynomials, or the non-deterministically polynomial problems. Now, these are problems where actually, as the size of the problem gets bigger, the length of time it takes to solve them extends very, very quickly. This is exponential time speedup, or Fibonacci time speedup. But the thing that these problems have in common is that if you've got an answer, then you can check it very quickly. So an example of this would be factorization. One of the reasons why we use factorization for cryptography is precisely because it's this kind of a problem. You can take two prime numbers and multiply them together to get a composite, and that takes no time at all. But if you're trying to find the factors of that composite, that's a very hard problem indeed. So this is perfect for cryptography. But there's a class of problems even bigger than that. And these are the problems where not only are they exponential speedups or exponential slowdowns when you're trying to solve the problem, you can't check them either. And so this is things like the traveling salesman problem. Excuse me. These are the NP-complete problems. If you've got a traveling salesman problem, you can try and find the answer. Is it the right answer? Well, the only way to find out is to solve it again. But that's not where it stops. There is a class of problems even bigger than that. And it's so big we don't really even have a name for it. These are the problems which are so big. All of these previous problems assume that you can enumerate the cases. We can find every single path through the cities, for example, in the salesman problem. But some problems are so big that we can't even do that. They're continuous valued, for example, and these are things like protein folding. You can't even count the number of ways the proteins can fold. And it would seem that quantum computers are going to be very good at solving some of those. Now, let me give you an example of the kind of problems that we're really interested in solving. This is a picture of ferric sulfide. These are the chemical pathways, and ferric sulfide is very interesting to us because it's part of an awful lot of biological processes. This is what this picture is trying to depict. Now, we can model this on classical computers. We can model that to within an order of magnitude. That is, we can get the decimal point in the right place. Now, all of the rest of it, we can't model at all. And we're very interested in being able to model this. And there are lots of problems like this, things like electron fields around molecules, which have got a lot to do with fundamental chemistry. All sorts of things that happen inside atoms are very interesting to us, and we have no way of modeling them. And we've known this for quite a long time. In fact, our story really starts in 1982, when there was a conference. It was organized by physicists to try and understand how they could model these quantum effects that they were discovering more and more about. And nobody really had any ideas what sort of approach to take. But Richard Feynman was there. Richard Feynman, you probably know who he is. He was one of the architects of quantum theory. And he said, well, if you're going to try and model a quantum process, you're going to need a quantum computer to do it on. It's the first time the words had ever been said. And nobody had any idea what that even meant. But it got people's minds working. And so it wasn't long after that, in 1985, David Deutsch developed what's called the universal quantum computer. Now, this is something like a Turing machine for quantum computing. It has set down the basics of what it even means to do a quantum computation. And we'll be talking about some of what he came up with in the course of that. At this point, it's purely theoretical, as is the Turing machine. It took a while, but Shor came up with his factorization algorithm. Now, we talked about factorization as being one of those very, very complex problems. Shor reduced it to log n. Very fast. All you needed was a quantum computer to evaluate it. But remember that we've based our cryptography on this. This will solve it. Then along came Grover's. Now, Grover's is a very interesting algorithm. What Grover's says is, let's suppose we take 4 cards, Jack, Queen, King, Ace, and you have to turn them over one at a time until you find the ace. In a classical system, with you standing there, it's going to take you 2.5 tries before you find the ace, on average. In Grover's, you can do it in 1 every time, guaranteed. Just turning over 1 card. You will always turn over the correct one. Now, so far, this is all purely theoretical. But in 2001, we got our first quantum computer. It was only 7 bits, wasn't very big. It took an awful lot of power. It was very unwieldy. But it ran Shor's. Shor's worked. All of that theory that up until then nobody had ever seen working, it worked. And that is when the genie was out of the bottle. Okay. That is the working part of a quantum computer. Down at the bottom, in the middle, you've got a tiny chip, which it needs to be very cold in order to work, about a third of a Kelvin. And all of the stuff that you can see around it are waveguides. They're carrying microwaves in to control the chip. They're carrying microwaves out to read off the state of the chip. There's refrigeration in there because obviously this has got to be cold. And then this thing is controlled, it's driven by banks and banks of equipment, which is keeping the system itself running. That's then put into a flask and taken down to very, very cold temperatures. And then the people who built it stand around looking very proud of themselves, as quite reasonably they should. So, what's actually going on in there? What's the quantum computer about? I'm going to be using this symbol to represent a quantum machine or a quantum state for reasons that you'll understand. And I'm going to try and make the distinction between the quantum machine and the classical machines that we're all using now. But effectively, what we're representing here is that whole assembly of hardware that you saw just a moment ago. And as you saw, this has to be connected to racks of machines, because that is what's keeping the whole thing stable. That's what's keeping the cryogenics working, and that's what's keeping the telemetry working. And then that requires somebody to sit and operate it. You need to set up the problems. You need to basically program it and interpret the answers. But this doesn't need to be in physical contact. The quantum computer that we'll be using today, the kind of quantum computers that you'll be able to use when you get back home, and there are quite a lot of them available now, they're all placed on the internet like any other service. You've seen people talking about AI services. There are loads of people offering GPU services. Well, you can get a quantum computer as a service, and we will talk about some of what's available. Now, for the quantum computer to make sense, you have to understand the basics, the thing about what happens in the quantum world, which is fundamentally different from what happens anywhere else. And there are two principles that I want to really explain to you. The first is the concept of superposition and collapse. You've probably done this experiment at school, but if you take a light source and you pass the light through a card with two slits in, then what you end up with is a pattern of light and dark bands. And this, when they first did it, this was the proof that light is wave-shaped, because these light and dark bands are created by the waves from the two holes overlapping each other and interfering with each other. That's not hard. You can see wave interaction in all sorts of scales. But what's interesting is that if you turn the light down really, really low, so you've got individual photons coming out, and it turns out that despite being a wave, light is made of little packets. When you turn the light right down, then those photons land on the screen over on the right, only where the light bands are. So the interpretation of that is that this one photon travels from the light source, it travels through both slits, it interferes with itself, and then it lands on the screen where it decides where to be. So right up until it's got to the right-hand side here, it's in a superposition. It could be in any of those places. It's in all of those places. It's a statistical distribution. But when it reaches the screen, and when we look at it, that's when it decides where it is. So that's the collapse of the superposition. The next photon, it's going through the same holes, it's interfering with itself in the same way, but it's going to land somewhere differently. And this is a well-established thing. We've seen this experimentally. We understand it's going on. It's not spooky. It's just how the quantum world works. The next thing is a little bit harder to get your head around. Let's start with that light source again. It turns out that when you're making individual photons, the process that makes those photons tends to make pairs at the same time. So, for example, if we look at the polarization, here is a series of photons coming out whose polarizations match. And we can test that the polarizations match because we can put a polarizing screen at the end, and what comes out is either a vertically polarized photon or no photon at all. And if you get a flash on one side, you get a flash on the other side. And if you get no flash on one side, you get no flash on the other side. And this is the proof that they're doing the same thing. But notice that even though all of those photons back there are in superposition, they could be in any orientation, what comes out is either oriented with the screen or it's not. There's nothing. And in fact, if we tilt the screens like that, the same thing still holds true. So what's really going on is that all of those photons are in a superposition of polarizations, and at the point at which it passes through the screen, that's when it decides what its polarization actually is when you look at it. But it happens the same on both sides. So what that means is that the decision that it's taken back here on the left, the easy way to think about this, it's not exactly like this, but the easy way to think about this is that it's taken that decision, it's passed it backwards in time, back to the source, and then passed it forwards in time again, back to this, the right-hand screen, and told it how to move. Like I say, that's not exactly how it works, but it's the easy way to think about it. This is called entanglement, and this lies at the heart of quantum computation. Now, this was the thing that Einstein said was spooky action at a distance, and he didn't really believe that it would work, but actually it does work. We've seen it many times. We're going to set up one of these states and play with it. Okay, now, quantum computers don't use photons. They use bosons, and we have an abstraction of bosons, which we call a qubit. A boson is anything with a spin-half field, and I will show you in a moment what that actually means. But the fundamental difference between a quantum computer and a classical computer is that in a classical computer, we've got two states which are represented, and they're represented very strongly. So if we want to represent a zero state, then we take a bunch of electrons, we take a charge, and we place it in one location. And if we want to represent a one state, then we move that charge to somewhere else, and the switch flips as a result of that charge. Now, in a quantum computer, we don't have that. We have a single particle, a single boson. And this boson is in one of two states. It's either spin down or spin up, and we can measure which of those two states it's in. Now, I've got some bosons here. Not real ones, obviously. You'd never see them from the back of the room. This is just a model. But this boson, this qubit, it's either in a down state or it's in an up state. And we process that, we compute by placing these into these two different states. But we can also place it into a superposition. If we put it into this state, we talk about rotations, it's not really rotations. When the boson is oriented like this, then what we're saying is that when we come to measure it, it will either measure down or it will measure up with 50-50 probability. That's probably going to be down but might be up. That's probably up but might be down. That's definitely up. So we're constantly handling these probabilities. But that's not the end of the story. See, there's something else that can happen. As we're doing these rotations, we can also rotate it like that. And what that does is it means that other different rotations change what they mean. So we've got, in addition to this, which is probability, we've got something called phase. And we can control the phase as well. And we'll see an example of how we're controlling the phase when we run the experiment. And you'd think that's the end of it, but that's not the end of it. Because actually what's going on here is represented by something called a Lie field. And the Lie field is expressed on two dimensions, which are upness and downness, and they are independent. So look, when the Lie field says it's down, which is out horizontally, that is the Lie field saying that it's in a down state. If we rotate it 180 degrees, it goes into an up state. But if we rotate it a further 180 degrees, it's down. But do you see it's changed color? It's gone into a sort of an anti-down state. And when we rotate it again, it goes into an anti-up state. And finally, it goes back into its original down state. So 360 degrees of rotation gets you into sort of a mirror image. It takes 720 degrees of rotation to get back to where you started from. I can demonstrate that with this teapot. You never thought you were going to see people juggling teapots, did you? You can see the picture on the front of this. If I want to show you the back, I can show you the back, or I can show you the back like this. But if I want to go around all the way, you can see the front, but you see how I'm all twisted up around it? I have to go all the way around again to get back to the starting point. So 180, 360, 540, 720 degrees. That is the Lie field, and this is a Lie pot. Okay, so we start off with a boson in some state, a qubit in some state. The way we measure it is we pass it through a magnetic field. So here is a nice strong magnet with the field passing down, and then we literally push the boson through it. Now, as it passes through, it takes a decision, but it's entangled. So as it takes its decision, as it gets measured by that magnetic field, it passes that measurement back in time to the original place where it started from. And so this is the power of the quantum computer. It means that we can do computations using results that we haven't got yet because we haven't finished computing. But what happens is when we do compute it, the result gets passed backwards in time, and then it affects the subsequent computations that came from that left-hand qubit. Now, I'm not expecting you to understand this, but what I am trying to do here is to illustrate the power, where the power of these computers comes from. If this is not making sense, then just stop me and ask. Okay, so how do you use this machine once you've built it? Well, the first thing that you do is you construct some problem definition by creating a bunch of qubits and initialize them into some state. And probably that state is going to be some kind of a superposition. But then what we do is we transform the problem by doing further rotations, entangling them together. That's the program. And then finally, we collapse it right at the end, and we generate a result. But this is only one possible result. Remember that photon landing in all of those different spots. We rinse and repeat. We keep on doing this because this is a statistical process. And gradually, what happens is the answer that we want, or the answers that we want, start to come into focus, one after another. Does this make sense? Would you like to see a demo? Good, because this would be a real short talk if you didn't. Oh, there I am. Okay, I'm going to have to keep stepping back to the keyboard to show you this, but effectively what we've got going on here, along the top middle, you can see a series of lines. This is called the staff, after musical notation. What's happening is that qubits are being generated over on the left, and they're all coming in a down state, like so, and then they pass from left to right until they reach the end, and they fall off the end, at which point they're measured. The result of that measurement appears at bottom left. And we haven't got a measurement there at the moment, but I'll show you a measurement happening, because actually nothing's been injected and nothing's been measured. There's other stuff in there which I can show you, but no, this is hard because my screen's down here. Now this is a NOT gate. That, whatever the state is, it inverts it. And you can see several things that have happened. If you look at the cartoons on the right, you can see that's the actual measurement that's taken place. So most of these, they're empty. Most of those circles are empty because these are definitively in a down state. But the top one, it's full. It's saying the probability of this reading a 1 is 1. You can also see another little line, and that's representing the phase, and we might see that phase changing later on. But at the moment, you're just seeing these states. That's it. Now what we have here is a Hadamard gate. What that's done is that rotation. So again, you can see the effect on the cartoon on the right, and you can see that it's in this 50-50 state. The phase is still 0 degrees, but you can see over there on the right-hand side, on the left-hand side, you can see the results that have come out of this. You can see that the measurements that we've taken are 50-50 divided between 0000 and 0001. And so this is representing the fact that bit 0 could measure either way. If we put another Hadamard gate on another bit, then you can see we've got 2 bits that are in this superposition, but they're operating independently. And you can see now that our results are evenly divided between 4 output states. This is all exactly as you expect it to be, right? So now I'm going to show you another gate. This is a conditional knot, or snot to its friends. Now what this gate does is it changes the state of the bit that it's sitting on depending on the state of the other one. So this is like, almost like an exclusive OR. So if we now put another NOT gate on Q0, then you can see they've both changed. And so now the only output state we've got is 1, 1. And that too is as you'd expect. We've got one which is conditionally inverting, the other one which is not. But what happens if instead of putting that one in, we put a Hadamard? There you go, that's the Hadamard. There you go, you need to see this. Now, do you see there's only 2 output states now, not 4? What's happening here is that first Hadamard gate is choosing, it's basically putting it into a superposition. It's 50-50, it could go either way. But the second one is inverting it based on what it turned out to be. So if this measures 0 up the end, if it measures down, then the snot doesn't invert it. If it measures 1, then the snot does invert it. So what's happening is exactly as you saw in that double photon experiment. Q0 is going right over to the right-hand side, getting measured, and then that measurement is transmitting back to the snot gate. The snot gate is then doing its job whether or not, and then the result is being sent across. And you can see that these two, they're bound together. They don't have independent existences anymore. And you can see that because the outer circle is shrunk. That says this is an impure state. What you're seeing here is called a Bell state. And the Bell state is the computational equivalent of those polarized photons that you saw earlier. So this is a very, very simple demonstration of what the quantum computer does, and it gives you an idea of the kind of things it works with. This is not useful. This is Hello World, and Hello World is never very impressive. But let me show you an example of an actual task. This is a quantum teleporter. Now, it's a true thing about the quantum states that you can never replicate them and you can never destroy them, but you can transform them. So the task that this is doing is we have Alice on the left and Bob on the right, and they are separated in space and time. Alice wants to transmit her quantum state, which is at the beginning of Q0, and you can see right over on the left, we're constructing a state, and you can see that state being measured on those dials, just about here. And we can obviously change that state. Now, that's Alice. Completely independently from this, in the second bar, we're creating the Bell state that you saw just a moment ago. And so we've now got these 2 bound photons, 2 bound qubits together. And then what we do is a little bit of computation on it, the result of which is 1 bit, 1 qubit, which is Q3, and you can see that being measured in the 3rd instrumentation. But it also produces 2 classical bits, which they're just ordinary bits. Now you send those 2 bits and the boson all the way over to the right-hand side, all the way over to Bob. Can we get a microphone? What does?
So the point is that from qubits, we are building gates, from gates transistors.
Yes.
And from transistors, we are building controllers and then processors.
Yes, exactly. Okay. And so this is one of the things that Deutsch did. He created this model of quantum computation, which was a huge simplification of the quantum theory, but captured the idea of quantum computation in the same way that the Turing machine is a huge simplification of electronics. You don't need to do very much electronics to do computation. Yeah. In the same way, you don't need to set up quantum experiments to do quantum computation. You're using this approximation.
So the qubits will follow the digital gates transistor a baseline in order to calculate something.
I'm sorry, I'm still not hearing you.
So the qubits, when we create transistors from qubits, this will follow the baseline of the digital electronic that we still know.
Maybe. I'll talk about that in a minute.
Ah, okay.
Okay. Here's the important thing about this that I wanted to show you. You can see that the result at the output of Q2 is identical to the state on Q0 that we made right at the beginning. And if I play with that, you'll see it change. But in order to do that, we have transmitted this 1/2 of a Bell pair. We've also transmitted those bits, those classical bits. If somebody gets in the way and tries to tap that, then they can see the state that's being transmitted, but they can't decode it, because you need those classical bits to decode it in the right way, so that when you do the measurement, it gets transmitted back correctly. If somebody gets in the way and tries to steal that qubit and tries to interpret it, then they destroy the state. It's not only that, Alice can see that somebody's in the way, Bob can see that somebody's in the way, and the somebody who's in the way doesn't get to see the message. He doesn't get to see the state. So what we've got here is an example of absolutely guaranteed, secure communication. And in fact, it's this technology that's being used by the Chinese to communicate between their embassies around the world. When they built the quantum network in New York, in the subways, this was what they used. This is a genuinely useful algorithm, which is, and you can see it's quite a small one. You don't need a great deal of computer power in order to make it. So even on a very simple toy simulator like this, excuse me, even on a very simple toy simulator like this, then we're seeing useful work being done. And in fact, even on this simulator, there are quite a lot of research papers that have been published on the basis of these kinds of simulations. Now, I know we're running out of time, and I wish I could show you more of that. This is where we were 5 years ago. Since then, obviously, there has been a huge amount of excitement. Loads of people are producing loads of reports, loads of research, lots of investigations. Fundamentally, what they're doing is they're looking to try and find bigger computers. There's a thing called quantum volume, which is the number of bits you've got multiplied by the length of time you can keep them coherent. More players are coming into the market. There was Google and IBM originally, and a few universities. Amazon has now got a quantum computer development process. Honeywell, whoever thought they would be in this space? We're trying to get more stable bits. It's turning out that we can do error correcting bits so that even if they decohere, then we can get them back on track again and sort of retune them. And people are looking at lots of different applications, of course. Cryptography is so important, I can't not talk about it. But simulation, imagine if you could simulate the traffic flow of an entire city, no matter, every single twist and turn that could possibly happen. Design, simulations, optimization, and I bet you thought this was going to be the only talk that doesn't talk about this. It has obvious applications in artificial intelligence, because artificial intelligence is all about this massive parallelism, and here we get massive parallelism just as part of the basic way it thinks. So this kind of brings us up to date. So let me show you this. What I'm doing here is I'm plotting, this is, over the last few years, this is the size of the actual working computers that have been built and are running. The red dots, ignore those for the moment. This is D-Wave. They're not building a computer quite like the ones that we're looking at. That's an annealer, which is based on photons. So they're getting very, very large numbers now. But it doesn't do all of the kind of computations that we've been looking at. But all of the other ones, those are genuine Deutsch-type computers. And if I draw a trend line through these, then you can see they're pretty happily on these two trend lines. Now that trend line, you'll see that this is a logarithmic scale. This is a doubling of power about every 18 months. Does that sound familiar? Now that Moore's law is sputtering to a halt, we've got a new technology coming up which is showing the same sort of thing. And just like Moore's law back in the 60s and the 70s, that we have no idea what the physical limits are going to be. We can keep this up for totally the foreseeable future. So my question to you guys is, if you take what you know now and you were transplanted back into the 1950s, what would you do with that knowledge? But here it is. The same thing is happening all over again. And who is going to program these things other than us? So what has actually been going on? Very, very quick summary. A lot of engineering. We have been trying to scale up. We've been trying to build bigger computers, and we're trying to basically keep them coherent for a lot longer. At the moment, they're operating very cold, but there's a lot of interesting chemistry coming on, which is going to allow high-temperature superconductors. We know that we can build superconductors that run at about 90 Kelvin. If we can get up to about 150 Kelvin, that's the kind of temperature that you can put cryogenics on a chip. So we'd be able to have a quantum security chip in a laptop. And that doesn't seem to be far away. We haven't got it yet, but it's certainly within sight. There's been a lot of applications being developed. Obviously, physical modeling like chemistry and the weather and stuff like that. All of these very large systems, which are very, very difficult to simulate right now. There's a whole range of optimization problems, particularly for things like traffic flows. And one of the things that a quantum computer is able to do is, if you imagine a city transportation system, you imagine the perfect storm of accidents and signal failures that will come up the system. The quantum computer will take you straight to that and show you how to fix it. Financial. Any of you in the finance world will know just how complex the models are and will know just how much they're interested in handling risk and marginalia. And this is the kind of technology which is very good at handling that. And of course, I mentioned AI. Security is obviously an important thing to be aware of. Right now, the security services around the world are slurping up messages which they can't decrypt because the keys are too big, in the hope that in the next few years, they're going to be able to open those envelopes using quantum decryption techniques. Probably a lot of those messages are going to be available in about 5 years, certainly within 10 years, the rate of current improvements. But the quantum system gives us with one hand and it takes away with the other. So what we're looking here, there's a lot of theories about how to build algorithms that are secure against a quantum attack. And at the moment, there's a competition going on. Just recently, there's a short list of 3. And just recently, one of those, it was called Rainbow. It was suspected to be, it was a very promising thing. And they found that, yes, it was absolutely quantum secure. But they cracked it classically in 2 weeks. So that came off the table. But there is a lot of work in this field. But of course, as you've seen, there is also quantum communication itself, which is provably and definitively and absolutely uncrackable just because of the way the physics works. And so a lot of the stuff that's going on in the engineering, I believe in 5 to 10 years, you will have a quantum security chip built into your laptop alongside the TPS chip, for example. I've got the last few seconds, so let me show you some resources if you're interested in this. The one in the middle, Nielsen and Chang, is the absolute classic. It's a big book. It's a bit out of date now, but it tells you everything you need to know to get started. It approaches it from lots of different sides. It shows you how the machines work. It shows you the mathematical foundations. It shows you a lot of useful algorithms and a lot of useful programs. It's an absolutely superb book. The one on the left, Quantum Computing, A Gentle Introduction, it lies. And the one on the right, Quantum Field Theory in a Nutshell. If you want to understand why this stuff works, if you want to understand what the fields are, this is the book. But I warn you, it is a very big nutshell. The computer that we've been working on was provided by IBM. They have terrific resources. They've got the simulators. They've got machines up to 50 bits, and I think you can get 10 minutes of time on them for free. Now, 10 minutes is an awful long time when you think that a run is a millisecond or less. You can get a lot done in 10 minutes. And that's made freely available because they really want to get people involved. Amazon and Google, they also want to get you involved, and so there are some very good resources. And if you can't find anything else to look at, there's always Wikipedia. I'm out of time. This is all I have to show you. Thank you for your time.